Welcome back to EPE Live here at the Rottler headquarters. I'm Ryan, and today I've got my dear friend from Digital Metrology, Mark Malburg. Mark, how are we doing today?
Hey, we're doing great. How are you?
Yeah, it's good to see you out here in the Northwest.
Yeah, it's good to see you smiling that much, too.
Appreciate that. We're here today. Mark, you have a vast knowledge and history, and you've been around our industry hanging out with us. How many, 4 or 5 years now?
Well, you guys 4 or 5, the industry as a whole, like 34 or 5.
Yeah,
absolutely.
Yeah, which we're going to touch on that. And your story and just your background, I know people have seen you. You've been at PRI with us. You have a history in manufacturing engines from the OEM large scale and all the way down. It doesn't matter if it's a 3-man shop or a 3,000-man shop. You're in it. But you also do a lot with your background and your experience in things, all things measurement, metrology.
Sure.
So just run me in. How did you actually get digital metrology, the background? You've got all these things going on.
Yeah, well, honestly, I got my start in plateau honing. Literally, my master's thesis was in plateau honing. So this has been part of my life since I was just a baby. But yeah, I spent 10 years at Cummins as their corporate surface metrologist. So through the 1990s, just about, well, literally any surface on an engine was under my umbrella. And in the late 90s, so many industries and other people were pulling from me that I left to form Digital Metrology. I left on great terms. Cummins is still, great friends of mine. And I get to meet some really cool people now, so you guys included. I'm the happiest dude on the earth. Someone asked me a few weeks ago, what was your favorite job? One of those icebreaker questions. And I said, today. Absolutely. I love what I get to do. To your question, I work across a lot of industries. So I'm working in consumer electronics, sporting goods, optics, paper, spaceships, pick an industry, and they probably have surfaces.
And and you go in and you help them out, and you also get to learn. I mean,
yeah. So that's the scary part. Is, hey, Mark, can you help me? It's like, I don't know what you do. But often we can find a common language. I can help them describe their need in terms of a geometry. So the quick thing to, and I'm rocking out of this. I'm going to pretty soon be backwards to the camera the way this chair is spinning. So if you see the back of me, I still love you guys. The cool thing is I can help someone start to explore what really matters. We think it's too rough. Well, maybe it's not too rough. Maybe it's too lumpy. And I'm going to use weird words like that with people to get them trying to not be so technical, but be more human. Unfortunately, you guys have a left brain and a right brain, the analytical and the artistic. So much of what I deal with is the artistic side, and people are afraid to use it. There's a surface spinning on the screen right now. You guys recognize that? Some of you do locally. Yeah, that's where we are right now. Okay. That was an observation you just had on the total non-technical side of your brain. And that's where I like to bridge that with my customers. I walk into a place doing plastics. I don't know anything about injection molding, but I can help them describe things through surfaces.
And how is that, I guess, for me, and we were talking about this last night, and, I was telling you, I background's mechanical engineering, went to school for that, measurement, you touch on, you just scratch it, but you also learn a bunch at the same time. And metrology and the science of it and measuring, how is, one of the things for me as an engineer that I'm, always trying to remind myself is don't solve something that didn't need, or don't design something that didn't need to exist. Mm-hmm. How is, you get to see all these different industries, and you get to see, the core being measurement and how you measure, and there's all types, and you're trying to relate. You put it in a unique way. You're trying to relate with your customer and take that approach of, we don't need to sit here all in this theory, but let's talk about things like lumpiness. Let's talk about that. Yeah. How of those industries, you're able to draw on that experience, and what's that like? And you might see something over here, and you find those applications and carryovers?
A great example is, I work in gaskets a lot. Mm-hmm. In sporting goods, it's the same concept of a tennis shoe on a tennis court. The way the rubber conforms of a shoe on a tennis court is the way a gasket conforms on a head deck. So those kinds of concepts translate around. Some of the curvatures we deal with on a, let's say on a rolling element bearing, we hate waviness. Waviness, that lumpy thing, causes stress. So if it was a nice smooth curve, that's great. But if there's a little wart along the way or a dimple, not even in roughness, a little lump, that's a huge stress causer. Well, that same thing on a gear is a noise causer. So there's a lot of crosstalk when we start thinking about shapes in a more primitive way. Stop thinking about numbers and think about the shape.
And you've done this really well. I mean, your software and digital metrology and some of the things you do, which is amazing. We use it all the time, right? We've partnered together to incorporate it in the hones, and I've called you multiple times to use it in different applications and use it on cylinder head surfaces. And we're looking at and one of the things you originally said, you're like, we want to look at the image.
Yes.
And I would, being trained in engineering, and you'd say, no, I want to look at the numbers.
Yeah.
I'm just going to look at the numbers.
Sure.
Right? And I think we do that. We want to simplify, but surface finish RA, then you now RZ, the plateau stuff, and you can just get so into the numbers.
Right.
And do you feel like you miss things when you do that? Would that be the point there that you're?
Yeah. So we're going to jump around today. You told me I get to do this.
You do it.
All right, let's do it. So we're going to jump around. Would you really want to look at the numbers to distinguish sound? Those are both 105 decibels. A chainsaw and a concert can't be distinguished by the numbers. And if we can't distinguish a concert from a chainsaw by numbers, how do we expect to, which way am I going? This is the bouncing around part that I thought I had a slide for. I did. Geez, Mark, where did it go? There it is. Those surfaces all have the same roughness. So trying to put a number on a shape is a losing proposition. We can't really describe nuance with a number. And there are an infinite number of shapes that would have the same, quote, roughness. I could put all the lumps on the left-hand side and all the fuzz on the right and still get the same number. So we do far better, and here's the key, is the last performance we're trying to suck out of things anymore is in this space. One of the favorite things I heard was kind of a summary of how we've designed things in the US. And we used to design things by size. If it's the right size, it'll fit together. Well, that was great for a few hundred years, and then in the 1970s and 80s, that wasn't enough. So now we have to put them in the right place. And we started talking about, are they square? Is the bolt hole pattern equally spaced? Are we putting the right size in the right place? And that gained us more performance as engineering as a whole. Today, the performance all remains in this shape domain. We've used up the easy stuff. And now to do better, and Darren's talk was a great example of how shapes are absolutely critical to getting that last performance out of things. It's no longer a diameter is good enough. It's what's going on in the shape space.
Would you say, on the shape thing, and we talk about the tools, which is, part of why I wanted to have you here today.
Sure.
Is the measurement devices that we have in the engineering exchange. There's so much out there.
Right.
Now, in this world, in engines, where micrometers, dial bore gauges,
Yeah.
profilometers, we've done a lot of work, and so many people are using that now.
Right.
But there's scales to that, too.
Sure.
I mean, for me, and my question on this is measuring shapes. And you've seen this. I got to rely on you here. I mean, I get the Mitutoyos, the Zeisses, the big brands that is what they do. They do measurement devices, and they come into Rottler every other week, and they've got this tool and that tool, and what do you see? I mean, the conversation, every shop that I've been into that's at a large enough size, or any OEM, right, like a GM or a Ford, CMMs,
Sure.
right, and that isn't necessarily relevant to everybody here.
Right.
Is there am I missing something in that? I guess would be my, I always look to you and say, I don't know, do I need it? Do I not? It does look really cool when you
Yeah.
see it, and it gives you a lot of data.
Sure.
But, what's your what have you seen out there, and what's your takes on where do you fall with measurement devices? And
Yeah, so let's play for a minute together with what is out there. In the world of measurement, first off, some shapes that really matter might be, are these things round or flat or straight, or do we have cylindricity, or, are balls spherical? So in that shape world, you can do a lot of things. Let's start out with surface finish. We measure surface finish every day with our eyes or our thumbs or even our butts when we sit on a chair. We can go from there to, say, a skidded gauge like the Mitutoyos you guys sell, up to Skidless or all the way to optical. We can spend anywhere from $2,000 to $500,000, literally, to look at something like surface finish. The question is, what shapes matter to you, and where is that investment worth something? It may be that your eyes are good enough. For example, with your eyes and maybe a small microscope, you can look at a damaged part and see that the damage is uniform, and maybe it's speckled. Oh, that might be something versus striped. So there is a lot of money we can spend, but there's so much benefit to your eye when it comes to surface finish. And we tend to rule that out and think it's not as important. It's ridiculously important. The surface finish is the fingerprint of the last thing that touched it. Whether it's the manufacturing process, the mating component, use your eyes. Don't be afraid. Don't jump to numbers. That's the engineer syndrome, is I need to get it into a spreadsheet and do statistics. Numbers are garbage, like I showed, with the chainsaw. So the amount you spend maybe is the amount of risk you're willing to take, but I'd say trust your eyes. That's the simple one.
And you talk about, it is amazing, right? I mean, we can feel things, and we all scratch our finger like your speaker on your computer here, right? And you can feel that, and you say, that's probably rougher than the smooth surface.
Let me interject real quick. We tend to discard that as not as important, though. That's really important. Yeah, keep going.
Yeah, and so I remember when surface finish in a 32RA. My dad being a machinist at Boeing. And
Yeah.
You still can get them. I'm sure you probably have a set. You have the little bifold thing. You open it up, and it's got
one in my backpack.
Got a little surface, and you set it next to it, and
Right.
you scratch this, and you scratch this, and you
Yeah.
say, how accurate? For a quick pass, it is an okay start. Do you run away from it? Do you still use it? Depends. You're going to say depends on the application, right? But
if I was stranded on a desert island, I might use it because, I have to measure roughness on my desert island, of course. The numbers on them are pretty bad, but if that's your tool you've got, use it.
Better than
That's
nothing.
better than nothing, absolutely. I mean, that's like saying, well, I don't have a gauge, therefore I'm going to put a blindfold on. No, you're still going to use your eyes. So use what you've got. Yeah, it's a case, I think the real value is in the interpretation, not the measurement. I joke that toddlers know more about surfaces than most engineers because the toddler put the surface in his mouth.
my 8-month-old is very acquainted with my floor, so I hear you.
Yeah, absolutely, you get that, right? So yes, they have a deep, intimate relationship with their surfaces where once we turn it into a number, we've lost all the information. We've lost the story.
So, just playing with that measuring surface finish.
Yeah.
We're on a desert island, maybe that's that level. Mitutoyo, SJ210, skidded profilometers.
Right.
And, we've done a lot of discussions, and I don't want to spend too much time. There's different styles and variations. The skidded being it can only measure roughness.
Yes.
Right. And so, in my question on that, and using an example of a cylinder head.
Right.
And I get this a lot with the larger corporate companies, the Caterpillars, the Packars, the Cummins. And if I get a spec and written by an engineer, I'm usually anymore, I continually see waviness.
Absolutely.
And in WT and some of these, could you elaborate on why are they looking at this? How is the lens through that world? Because I don't get to see that.
Sure. So let's do it this way. So first off, you guys are measuring typically with a skidded gauge, like the Mitutoyo SJ210. Those two graphs represent the information difference. A skidded gauge has this big chunky thing down here at the bottom that rests on the surface with a little diamond poking out. So that big thing sits on the surface like my hand sitting on the desk when I write a check. My fingers are wiggling up and down, but if the desk is shaking, my hand shakes with it. Well, because of that skid, if the surface has lumps in it, the skid goes up and down over the lumps, and the stylus doesn't even know what happened. So the surface could be very wobbly, wonky, humpy, lumpy, whatever you want to call it. I'm not going to use technical words because I want you to think like the 3-year-old. Those lumps will not show up on a gauge like the SJ210. The skid follows them. But this is going to be epic, literally, because I'm going to epic. Those two surfaces have the same roughness. They have the same, quote, waviness. They do not show any difference when you're trying to measure them in production, but one leaks. So that shape, that wavy shape along the way, those are leak areas, and a skidded gauge, like you guys use, and they're affordable, they're fast, they're easy, will not see that. That is the area right now where we're optimizing and trying to do better and better when we design, is we're trying to design in the OEM level for low cost. We're not going to over-specify flatness. Make it ridiculously flat. Well, guess what? Ridiculously flat doesn't matter. Controlling waviness is what matters. Gaskets don't care if an entire surface is bowed. I think I've got a pic of that it's the shape of it that makes it seal or not, just like it's the shape of the art that makes it interesting. It's not the height of that statue that makes it beautiful. Similarly, it's not the height of that curvature that makes you leak. It's the wiggles along the way. Gaskets bend. What? I know, it's mind-blowing. The same thing applies to things like crankshafts and bearings. Things are going to squish at the larger scale, but they fight it at the finer scale. And that's, again, if we just step back and think about what's going on and try to not constrain ourselves to say, how straight is it? I don't care how straight it is. I care about how does the mating component feel about squashing into it or squishing. Squashing?
Or either one works.
All right, okay. Well, you're the expert. You said you had an engineering degree. So, yeah.
So, if I'm sitting here and I think this image is a wonderful example, and but anybody doing honing or performance engines, they're going to torque plate hone, right? And we know we need to load up the deck and I guess does that what's the effect or when I'm taking these traces, right? Even if I'm using a $1 million CMM,
sure.
I couldn't do this with a torque plate on, so I guess what's my correlation? And I mean, how is there a method? Fuji film is a thing. Is that
Fuji's great?
Yeah.
I'm a huge fan of Fuji film.
Okay.
So it's a pressure-sensitive material that when you squeeze it, it bursts little bubbles and makes color. And if there's nothing squeezing in an area, you don't get color, and it's very powerful. I think I've got some from Zach here. Epic. Let's go to that. For those of you who haven't seen it, this is some Subaru stuff. And you can kind of see the light spots where there's less contact pressure. And it doesn't burst the little bubbles in the paper. And we see that, in this area, we've got really good pressure, and over here we don't. Very, very useful, rather affordable way of doing flatness. And by the way, this data right here, that came from a $250,000 optical system. We can buy a lot of Fuji paper for that.
Yeah. And is there a brand that's for someone?
It's actually become more like Kleenex. You can just search for it.
Kind of the deal.
And they're brands. So understanding shapes and how your surface feels about it is far, far, far more powerful than trying to put numbers on things. Because your experience, your touch, your feel, your dyno is going to tell you 1,000,000 times more information than Taylor Swift versus a chainsaw with our numbers.
Let me, and I think, and I see this at that OEM level all the time, and there's this spec, and GD&T, engineers love that, right?
Yeah.
GD&T and flatness and surface and roundness and concentricity and true position and all that. But in an engine, it's a dynamic thing. We were joking about calling it an explosion. That's a combustion event.
Okay, it's an explosion.
But
explosion.
But how do you, I guess the question always for me then, it's something that's so fascinating about working in engines and specifically in the remanufacturing, the aftermarket,
right.
is you have manufacturing, you have process, like you said, and that you're going to leave that fingerprint.
Yes.
And I always say that take a cylinder bore or something, or any hole. Nothing's a perfect circle. I'm always like, it kind of starts as an egg, and then these go out and live their life in their applications, and then egg becomes more of an egg, and it's living, breathing. It's got this dynamic thing going on.
Right.
So it's so interesting because you could spend $250,000. You could get this trace, and you can see all this, but I mean, it's almost like it's that simple. Sometimes I guess it's the right tool for the right job is the question. And maybe for engines, that Fujifilm, does that maybe give me a little bit better of a picture versus, I'm not sure if this is applicable or if, for what I'm probably trying to do, because I'm not head bolts and the distortion that they put in there, it doesn't show that.
I love the language you're using because you're talking about head bolts and distortion, not flatness.
Yeah.
Because somebody says, well, that causes a flatness problem. You know what? Head bolts and distortion may actually be less than the bow that we see in that surface right now.
Oh.
They're local little ripples in the midst of the big one.
Okay.
So the fact that you even mentioned that is awesome, because let's start thinking at the scale of the gasket between the head bolts instead of at the scale of the entire deck and is it bent or not. So our numbers out of a CMM and those kinds of things are often how flat is it, not how lumpy or wavy, sorry. So the questions you're phrasing a question in a way that Fuji paper actually answers better than the CMM. And I'm going to take you a yes and. First rule of improv is yes and. Yes and worn parts are often your best indicator. Look at that surface afterwards and see where the contact was. We've learned so much more about cylinder bore distortion and torque plates by looking at lightly used engines than trying to predict it by measuring it.
More of an empirical model is better. Is more what you're saying is the test and then look at that and track off of that.
Where is the wear occurring? Where are the tight spots? What we find out, by the way, in a lot of our research is we spend too much time trying to make things round when oval is okay.
The question would be how much oval?
Well, that's Keith. So a piston ring can turn oval pretty easily. And there are tables for this. How much ovality can I tolerate? How much 3-lobe, 4-lobe, 5-lobe? Can you handle a pentagon or not? And by the time you get beyond oval into triangular, it goes way down. We can tolerate a lot of oval, but we can't tolerate 4 bumps. Think about head deck bolts.
Which is what you would get. And we've seen this certain walks.
Absolutely.
You put the torque plate, you bolt the head bolts on, and all of a sudden this thing has got 4 or 5 thousandths.
Yes.
You can see quite a lot inside of a bore. So.
And that's what our torque plate is doing for us. The real benefit is accommodating the bolts, not the ovality. Things are going to turn oval when they get hot and that kind of thing. And guess what? Ovality's okay. Similarly, a little bit of banana shape isn't going to kill us. Things are made to move, the way our Conrod works. So killing ourselves over something like straightness may not matter if it's the right straightness. So those are the levels where we're going now of, it's not just roundness. Forget roundness, it's roundness within every 30-degree window. Is it changing too much too fast? So back to the gasket situation, the gasket bends. A piston ring bends. bearing on a crankshaft squishes. So we tend to kill ourselves. And I'm going to hang out an unpopular opinion in front of the camera right now. People are spending way too much time making shiny deck surfaces.
Well, this is something I didn't want to touch on, and I see it all the way. And I mean, there's a balance, and for me
Absolutely.
being in this industry in 8 years, and even Darren touched on it earlier. There's sometimes you're spending time on things to make things look good, and looks do matter.
Absolutely.
I mean, you know, it's what's the end user, and sometimes that is a factor that I always, sometimes you have a person, or if you're selling a cylinder head aftermarket, and it's going to be deck, having it nice doesn't hurt for sell. It doesn't help doesn't hurt for business, right? But that's something that, again, that I'll see and I'm not going to name the companies up, but there are, and you know them, but there's certain large companies that some have a minimum and maximum in their tolerance for roughness, for
Absolutely.
waviness. Others only have a maximum.
Yes.
And that's always befuddled me, because I would think that, if we look at a gasket surface and in between the cylinder pores, there's nothing there holding that gasket together.
Right.
It's just friction. Right?
Yes. Yeah.
So to me, I would think that if you did get too smooth, do you see any of that happens in the stuff that you see, or have you seen failure modes between that, or maybe there's higher wear there because it was too smooth?
So there's a lot of discussion about traction. When you put a gasket in an interface, is it grabbing or is it going to slide and, have that micro threading kind of action? So yes, we see that all the time, and I don't think I know of a gasketed surface with only an upper limit in the OEM world. There's always a lower limit. We want some amount of roughness in that space. So people talk about roughness and make it better. Well, better isn't shiny, better is functional. And if the function is traction, then better means traction, not shiny. I mean, a lot of machinists brag about how good they made their surface through the eyes of shiny. Well, if the surface is supposed to carry a lubricant, if the surface is supposed to hold glue and stick to something else, if the surface is the back of your phone, it's got to have that sexy matte finish, better is not shiny. And we've got this idea that better is shiny.
Because it looks nice.
It looks awesome.
We all like to look at shiny
Well,
things.
and we've actually seen that in the biomedical world. Doctors want shiny implants. They want to put a shiny knee joint inside your body.
Well, I don't know, but I remember, and this is off topic, but titanium stuff was originally supposed to have a really rough surface in that world because the bone actually...
Well, they do rough where it embeds in your bone. They make it crazy rough.
Huh.
But the friction surface, if it's got a little texture, it holds lubricant and lasts longer.
Interesting.
But doctors don't think that's precise because it's not shiny.
We're all humans.
Yeah, so we need to think about a surface through the eyes of better, meaning functional, not shiny.
So and just to, in terms of flatness and waviness, because this is a big topic. It keeps coming up again, and I'm dealing with what are things that you see in terms that people do to, I guess, in the engine world, on the OEM side, or what are they looking at? Because it's all over the place, and as it trickles into the reman side and the aftermarket, what are those, are they having to change their machining processes? Are they having to take new approaches?
Yeah, so I'm seeing this, but I'm being really careful with confidentialities. I'm seeing it a lot more recently, in recent weeks. I've got customers dealing with leaks, people dealing with gear noise forever, and it's all about waviness, and people don't check waviness. Now, let me give you a quick definition here. We talked just a second ago about the SJ210. And it's a great gauge. I'm not dissing on the SJ210. I'm just trying to find a slide real quick of stall for me, will you?
Well, when I mean, the whole point of it, right? You're moving, I guess, going from the 210, you go to a 410 or something. And you look at this picture, right?
Yes.
And you've got this. I was thinking about it while you're there, and you're like, okay, I'm thinking about boats because we're here in the Pacific Northwest and there's
Right.
water all around it. It's like kind of the same thing, right? The boat goes in the waves, we feel the waves, and that would really be
Yeah.
rough. But you have the curvature of the Earth still, so
Absolutely.
and you're not measuring that. That's kind of the which does it. But in that, if I'm on my boat, I don't think I care much about the curvature of the Earth. But
Well, it's
when do I do versus
yeah.
don't?
So I mean, this is where that matters. If the gasket can follow it, it's the curvature of the Earth. If the gasket can't follow it, it's your boat.
Mm-hmm.
That's kind of the analogy. But this is where I wanted to go with this slide. And this is where we often miss this. When I talk about, and I'm going to use the words now, we're measuring a surface with a gauge like one of these. And when we talk about roughness versus waviness, your gauge measures roughness. Your Mitutoyo SJ210 is measuring roughness. If the stripe on the surface is wider than your thumbnail, 30 thousandths of an inch, if it's wider than that and you look at it and see a stripe, that's waviness. Through the world of surface finish, roughness, RA, RK, RPK, RVK, are all based on the fuzzy features that are narrower than your thumbnail. So we look at a part with a feed rate of, 50 thousandths. That won't show up as roughness. That's waviness. And we get this mode of, well, I see this surface looks rough. Well, if it looks rough, probably you're looking at waviness and your gauge isn't going to tell you. So the gauge is misleading. Those features on the screen right now for that data right here on my screen, I think those were 2-3 millimeter wide features. That's waviness.
That's not much. I mean,
That's very tight.
And you look at, and it's
Yeah.
anytime in data stuff, right? Even with this,
from
you
here to
you
here.
see a picture, we see these images, and you go, on a screen, it looks big. It's like working in CAD, right? And you go,
Right.
wow, that must be 4 inches.
Yeah, those.
But you're
those-
not talking that. You're talking 50,000, 60, a millimeter or two.
Right, 100 thou, 2
Yeah.
millimeters. Yeah.
Huh.
So when we're looking at a surface with our eyes, and that's where, again, I love to get people just exploring, forget the numbers, forget the math, and explore the surface as if you're going to rub up against it. Those things on the screen right now are 100 thou apart. Your eye would call that roughness. But here's the bad thing. That particular surface, those lumps, your eye will never see them, because your eye only sees slopes. Your eye only sees how light reflects off a slope. Your eye cannot see waviness. Humans' eyes will not see that. We need a gauge to measure it, or Fuji paper, or look at a used part. Be an explorer. Don't be intimidated that you don't have the $1 million budget. You have intuition, which is even worth more.
Well, you bring up a great point. And I mean, in the industrial diesel, high horsepower stuff, Cummins, the big engines, Caterpillar, yeah, and single cylinder head applications, you see a fretting that happens right at the top,
yeah.
right? Water hole repairs, all that, and it's from vibration and wear
Sure.
across that gasket surface. It's a great point of you can look at that stuff and say, well, that probably was the high spot, and now it's become the low spot, correct?
Right. Yeah, absolutely. The critical eye on a teardown is so valuable. That part wants to tell you a story. Absolutely. Yeah.
In terms of, the piece of equipment again, so, the big two to me, Zeiss, Mitutoyo,
Uh-huh.
Zeiss is everywhere. They're in your doctor's offices for optometry equipment, it seems. But
Right.
Do you have a preference personally, or just a question? Because it's a question that I think, when we see people with Mitutoyos, we see other people with Zeiss stuff.
Yeah.
Is there, just what's your thoughts and opinions on if I was investing in a piece of equipment like that, would you?
Sure. I can't because I work for all of them. So I'll say that much. Let's go here. So in the space, say, of skidded roughness gauges, there are lots of options. And quite honestly, they're almost all as good as each other. Their sensors are good. Apart from this top left pocket surf, they all use basically the same kinds of sensing, the same diamond. So I'm happy to just see somebody using something.
User preference would
User
probably what it would
preference,
come down to
absolutely.
in terms of it.
Similarly, in the skidless space, we have systems that range maybe from $10,000 up to $450,000. Yes, $450,000 to drag a stylus over a surface. Is that insane? $500,000 to move a little diamond across a surface. But yeah, that happens. And again, in this skidless space, everybody's using similar technology, similar sensors, very similar performance as far as what we care about in machining. So I don't make recommendations. Find one you love and find one you'll use.
I don't work for either. I like both. I have Mitutoyos here. I've used Zeiss stuff. I mean, I think both are. I think the important thing is to find something you like that is a reputable brand. Because, one of the things, and I'd hate to ever admit doing this, but if you put your settings wrong on a profilometer, you can get some pretty different.
Yes, you can.
So I think, when you see these, it's kind of nice, talking about shapes as opposed to the numbers, because it's very easy to look at the numbers or take these devices and take them like, well, that's the surface.
Yeah.
And the reality is, it might not be, because you're making assumptions when you have filters, all this stuff.
Yeah, so let's go there, because we had this conversation just a few minutes ago, I think with Darren. If we talk too much about numbers, you're going to get in the trap of my numbers are lying to me, my numbers don't repeat. And first off, surface finish, if we're in the roughness kind of domain, it does not repeat. If you have a repeatable roughness gauge, you likely have a dead gauge. Because we can move over 20 millionths of an inch and miss a bit of porosity and get very different numbers. So what I want to encourage you is, when it comes to surface roughness, think about the picture. Get to know your shapes. And that's where TraceBoss has been, part of that recipe is everybody sees their surface at the same scale over and over again. So here's a plateaued surface, crummy one at that, a little bit of dirt, what the heck. Okay, that's plateaued. We've got RPK of something on top. We've got an RK living in the middle here, and some amount of valleys, RVK, down here. We're happy. We're making it to some idea of a specification. But we happen to make a trace over a bit of porosity, and this blows up. RVK goes nuts. Whoops, RVK. And our numbers are all out of whack. But your eye can tell. Your eye says, oh, there's a ridiculous valley that might have been part of the material, not part of my honing process. The picture saves you from remeasuring and calling Ryan, calling Scott, calling whomever your guy is here, calling Ed, and saying, my hone's messing up, my RVK's out of control. No, your picture told you that's not the case.
Yeah, so I was working on a project for Caterpillar recently, and this is a conversation and this was happening. And my background and why I love having you in talking about this. When you take a measurement, and you take one, you go,
there it is.
I got a 16 RA there. I am pretty good.
Then or measure again until you get it.
Well, and I've learned that everyone in the world does this. We've had every manufacturing engineer and everyone that comes out there like, oh, you do that too. Yeah. And you're like, yeah. But what's the reality? I mean, is that lying or not? I think is a question that has to be answered, because I was, my kind of rule of thumb for measuring any, let's call it shapes at this point, I like that, was you're taking about 9 samples is usually what I'll do. And then I would average out off of that to give myself what I would say is more confident, or a student sample size if we're going to be in engineering school. But you once told me that there was a study that was done, and I think you said it was Volvo?
In Europe,
In Europe, and how they needed what was the sample size they had to take to say they could actually feel confident?
Sure. Yeah, so for one particular, any cylinder bore, so you're going to look at one particular bore, one hole. To get a statistically reliable number for, say, RK, RPK, RVK, took 32 traces averaged. 32 traces averaged before your number settles down enough that you can trust the number. And that's this problem. You know, one valley comes and goes and the numbers blow up. But I would promise you that anyone in this room, after looking at traces, looking at pictures for about, half a day, you would know by the picture if that surface is consistent or not, and it's just the numbers blowing up and down. The picture is something our body is really good at. I can recognize Ryan's voice over the phone if he's on a cell phone or a landline. It's still his voice. The signal's different, but I still recognize you as my friend.
Yeah.
And that's the same deal here. Make friends with your surface and recognize the picture. And when things come and go, you say, you know what, that's still my friend.
So it's a very good point. I mean, it's just something that it's hard. I mean, I love this because we actually use TraceBoss and those traces to back that up, because you would get it at, okay, well, I'm outside. It was RK was the number. You go, okay, well, you're getting, well, here's the thing. And
Yeah.
it was, that we're using that for those reasons. But, and it's, I guess the clarity is I don't feel like those things are bad surfaces. If you're using that and you're averaging your numbers and you're looking at that, it probably is a very good surface, but you could end up, and let's be honest, I don't have the time in the day to do 32 traces in 8 holes
yeah.
and say that my LS is all right. That's unrealistic. But, as an engineer, it's, taboo. But you are allowed to omit data.
Sure.
If you have a good reason for it, if you know and you can confidently say
Right.
that really, you're talking these minute details.
If there was a spike on it, you can't hone that. That's dirt.
Right.
So there is judgment. And again, what is the goal? The goal isn't the numbers. The goal is performance.
Mm-hmm.
And the numbers are only a guess, a stab at performance. Now, if I came in here with these same valleys and plateaued down farther, so there's only a little bit of valley hanging out, you would see that in the picture. Mm-hmm. The numbers are all going to move around. RK is going to blow up and RVK is going to go all over. Or if somehow somebody slipped you the wrong honing stone and we've got a lot more roughness in our plateau than we used to have, you'd see that. The goal in so many cases is muddied by trying to put a number on it. So, I just want people to step back and not be, my number's not repeatable, what are we going to do? Well, what you're going to do is do what a detective would do.
Yeah, I like that. I mean, it's to me, you have all this stuff, and that's really honestly. I mean, I deal with it every other week. I mean, am I missing out? Do I need this piece to do this? Waviness? Oh, I got to go. Mitutoyo's down the street. Do I need to go spend $10,000 or $15,000 for that? But I could use Fujifilm if I'm just working on. Maybe that's the right thing. And then I like this. Looking at a used gasket, perfect example, and you can see exactly where it is. And I think, but it is a training your mind and your eye to sit there and correlate that instead of just saying, well, clearly the coolant passage leaked here, to sit there and be more of a detective.
Yes.
And say, was that because there was a high spot? Was there was a low spot? Was there, something that happened there?
Sure. Look inside a bore and look at distortion. Your used bore will tell you, where the tight spots were. By the way, dial bore gauges are the bane of my existence. That measured bore right there is perfectly round with a dial bore gauge. Same diameter all the way around, just like a 50 pence coin is the same diameter all the way around. The valley on one side lines up with a peak on the other. But to your point, I want to play that out a little bit. Look at worn tracks. Where are the tracks on a worn surface? Well, this was edge loading, probably flat on flat, which causes higher stress, or maybe a misalignment. This is a great example. We were seeing stripes on a crank pin. The stripes weren't because of this dip in the straightness. The stripes were because of lumps along the way. Lumps along the way show up like those kinds of things, and your skidded roughness gauge does not see them. Let's all say that together. My skidded roughness gauge does not. Finding Nemo. Fish are our friends.
No, this. So the tiger striping here to see this, and you can see this.
Yes.
This is not magnified, or
that's actually a used part.
This is used part.
And when we see a used part where it gets shiny and dull, that means it was wavy to start with. Mm-hmm. And by the way, those stripes did not show up on the virgin part. Your eye can't see waviness until we polished off the peaks.
Interesting. So, you had some camshafts,
Mhm.
and we do that a lot. They're
Yeah.
main bores, camshaft bores, stuff like that. There's always this conversation, and, we talk about boring versus honed finishes versus this. It's almost, so take a crankshaft centerline, in my opinion. I mean, if you were in there and you were talking about, you can't see this stuff.
Right.
I've had debates back and forth with other of our colleague friends, and it's like, what do we line hone on these surfaces after we do it? Is the bore finish is good? You're putting a bearing back there, the heat transfer thing. There's all this thing.
Right.
But I guess none of that even matters if we're not even going to talk about waviness.
Yeah. So one of the things that's really not talked about in those spaces, because it's frankly hard to measure, is what about chatter around the circle? And in a crank bore, chatter is, in and out of lubrication. We put a gear tooth on a surface, and that's really tough. And it's one of those cases where almost the used part isn't going to tell you because it'll probably fail before you know it. We don't have great answers for a lot of this. You've got to be an explorer. If you're into a problem, I would encourage you, do some early hour kind of tests before it fails. Or if you're lucky, maybe look at an adjacent bore and see if the next door neighbor didn't blow up but has some fingerprints left behind. Roundness is a tough topic, by the way. I wanted to point this out here. Roundness really, really matters. And roundness in the metrology realm is typically measured with, on the left is a gauge with a precise spindle spinning around. You put your part on it and touch a little probe against it, and it's super precise air bearings. In the middle is a $500,000, 3/4 if you buy options, where you stick a probe down in your part, maybe it's an engine block, and you spin the probe around inside. That thing right there, you can kind of see a computer monitor that's about chest high on the left-hand side. That's a big, massive system, and that's really kind of the world standard to try to even begin to describe what you're talking about. It's a tough problem. Line bore, line hone, that kind of thing. It takes $500,000 to really see from a metrology perspective.
Yeah, it's always interesting to see, I don't have the answer. I mean, we were talking about this yesterday. I mean, you have this jury is kind of out, and you can see this in some of these tearings. Some of the stuff that the customers I've worked with have been, they're looking, and it's a teardown analysis that has led them to write a spec a certain way.
Absolutely, yes.
And sometimes that's good.
Yeah.
But also I've seen that sometimes where you get this, I need a 90-degree crosshatch angle on my connecting rod thing,
Yeah.
So I mean, I guess play devil's advocate here in a little bit of how do you transition between that? Because sometimes you'll look at things, and if you don't have enough of a sample there, then you could be.
Yeah, and I see some weird ones too. It doesn't really matter that you have a 90-degree crosshatch and a conrod. I don't know. I wonder sometimes, and this is Mark speculating, the views expressed by Mark Malburg are not necessarily those. Maybe they had a process that made good parts that happened to have a 90-degree crosshatch.
This is what I see.
Honestly,
this is exact the topic. Yeah. And I'm not, I'm one man's opinion and from manufacturing sides, and I agree with you because I like what you said about fingerprints. And let's stay on this.
Yeah.
If I'm honing something, I'm putting a crosshatch in. Let's take main lines.
Right.
Line hone it, put a crosshatch in there. Line bore it. Well, we know that
crosshatch.
A single point tool is going to, you're cutting a helix.
Right.
Now it's a screw thread. Does the bearing back out of that? Does the crosshatch hold it though? But if the crosshatch, the finish might be finer, so maybe it has less friction. I mean, you'd have to weigh all this out.
Right.
And then you go full circle and you go, I think maybe we just did what we did and it worked.
Right.
And a lot of times, there's so much stuff in the in industry and manufacturing and in the world that I think is that way. Yeah, I'm sure you've seen.
I see it all the time. So
more than me.
The crosshatched ones work.
Yeah.
Well, yeah, because those were honed. It's not
because
because
box of them sitting up here, and that
right.
was that deal.
Maybe it's not the crosshatch; it's the process. So yeah, I think that's probably a really good segue for our next guys, kind of connecting
Certainly.
process to function.
And that's
So-
what we'll leave that to that. But
Yeah.
I really, really, really do. It's always so good. We could spend
We could,
hours.
yeah. This is what we do over dinners. This is fun.
That's
So
really fun dinner parties with the families.
my wife's got this permanent eye roll. She,
Well, let's just grab a few questions. If anyone here today with us, is there any questions for Mark? So just to repeat for the cameras, the question being in between honing processes, the cleanliness before you take a measurement would be is the question there.
yeah. So I mentioned a skidded roughness gauge is going to follow any vibration. If the part is vibrating, the skid is going to ride it. And that's one of our benefits. The skid is a robust, easy gauge, and it's noise suppressed. If things are shaking, we're okay. Our biggest problem with a skidded gauge is the picture kind of on the left. If there's a little bit of debris, anything on the surface, maybe 20 millionths tall, a quarter of a hair, it's going to raise up the skid as the skid goes over it. And that means the stylus has to reach down farther. I'll use my laser. When the skid is sitting on dirt, the stylus has to reach down farther, and that's going to give us a fake dip in our data. I had a project 25 years ago where people were saying, our honing process is making holes in the surface. And they were referring to these things. That's not your honing process. You can't hone that. You're good, but
No, I'm not.
you're not that good.
I'll leave that to Ed and Scott.
Yeah, there you go. But there's the dirt. The skid raised up over the dirt and the stylus went down. Dirt will totally screw up your numbers. Here's the problem. The skid is big and it's wide. So the skid is going to see things and raise up, and the stylus is going to sneak beside them. If there's a little, piece of, literally a smoke particle. A smoke particle is 120 millionths. A smoke particle sits on the surface, the skid sees it, the stylus goes beside it, and we get data like this bottom graph. So yes, cleanliness is huge when it comes to measuring with a skid.
Would you, just to add on to that, I mean, do you see anything that you'd recommend for cleaning? I mean, is it brake? Yeah, I'll grab the brake cleaner.
Brake cleaner,
but
yeah.
I use rags, and the blue rags, they still leave lint. I mean, am I risking there, or
So-
should I blow out with air?
Both, anything.
All of it.
I wish I had an answer.
Get a clean room, downdraft.
In
Spend
this-
$500,000.
It doesn't happen that often. Brake cleaner, wipe it clean. Most of your data is going to be good. But if you see something like the top or the bottom, don't freak out. It's just a little dirt. You'll be okay. I'll talk you down. Call me. We'll hug. It's all right.
This is a better segue. The question being RMQ numbers, and Mark, take it away.
Okay. So my good friend just teed one up here. So we have a situation in surface texture where our numbers aren't very descriptive. Hopefully you can agree with me. Taylor Swift agrees with me that she doesn't sound like a guitar when you ask her. So the numbers are kind of bad, but we still need numbers, especially, if we're going to do commerce. I'm going to buy your hone that produces numbers. There's a situation where as a surface becomes more extremely plateaued, I'm going to move that down a click on the whiteboard here, see how repeatable my manufacturing is. So as a surface becomes more extremely plateaued, the RK numbers fall apart. They don't describe that surface well. Dr. Horst Bajfina, the author of the RK parameters, he said the RK parameters should not be in international standards because they don't work. They don't distinguish peaks from valleys when the surface becomes extremely plateaued like this. So here's a different way of looking at those two surfaces. We know those valleys came from some rough surface. Whoops, there's a valley down here. Sorry, we got to get to that valley and get back up. So there was some nasty rough surface we created to start with. We made it a very rough surface, and then we came in and finished off the peaks. That rough surface has kind of an amount of material as we slice our way through it, from 0 to 100% on the rough surface. The deeper I go, the more metal I will encounter. That's called the material ratio curve. It's in TraceBoss. You see it on the right-hand side. And this is where our PK comes from, and our K and all that comes from this graph. So there's a better way to deal with the extreme guy, the black surface in here. Instead of going 0 to 100%, we use a different kind of graph that turns that red surface into a straight line. It's no longer 0 to 100%. It's kind of stretched out on the edges. That space makes random into a line. And guess what? This random surface here, this little thin one, has a distribution of points. He has a straight line. So in the other graph in TraceBoss, you can switch to material probability, which will have 2 lines. In this space, this corner represents the amount of material where plateaus meet valleys. Super powerful. When people say, hey, Mark, take a look at my surface, I look at this number, RMQ. And in some cases, it may be 80%. Other cases, maybe 50% is where you want to live. That number is the amount of material under the peaks, which also tells me the amount of air underneath that for oil. So Ed asked me a follow-up to clarify more if you'd like.
Everybody asks, okay, where should my RMQ be?
Yes. We don't know that yet, but I will say this, that number is so much more powerful in describing what matters than MR2 in the K family, or the other numbers we might try to produce. This relates directly to how deep did I stroke the plateaus in. If I only stroked 8 times instead of 12, that number is up here and my RMQ is in a different place. So that number, maybe going from 50 to 80, is just a matter of a number of strokes or depth in your plateauing. Super informative number if this curve looks like 2 lines. Now, if that curve doesn't look like 2 lines on your screen, don't look at that number. So, yeah, that's the real segue to these guys. So we'll turn it over to them.
Mark, I really appreciate it. It's always fun.
Thank you for the
Digital
opportunity.
Metrology, Mark Malburg. Thank you, sir.
Thank you.